that implies that the limit as n goes to infinity of absolute a sub n, remember we're just naming this guy right here, a sub n, just as we named it, a sub n here, of absolute a sub n is equal to the limit as n goes to infinity of 2n squared plus 1 over 4 minus n cubed. Now, if you use an algebra 2 approach, the degree of the bottom is bigger than the degree of the top, therefore this sucker heads for 0. If you wanted to do a more algebraic way, you could divide top and bottom by 1 over, or excuse me, multiply top and bottom by 1 over n cubed, and you get the same answer. Okay? So this thing definitely heads for 0. Okay? Which implies, what does this imply? It implies that the limit as n goes to infinity of just a sub n, which is negative 1 to the n, 2n squared plus 1 over 4 minus n cubed, heads for 0 as well. Super useful tool, isn't it? That thing's powerful good. Now, let's go back to the one that I did before. Watch what happens here. Let's say that I'm looking at negative 1 to the n times 2n squared plus 1 over 4 minus n squared. Now watch what happens. Now think about this. If I take the limit as n goes to infinity of the absolute value of this, I get 2n squared plus 1 over 4 minus n squared, right? The degree of the top and the bottom are the same, so what I end up with is a negative 2. So this term turns into a negative 2 out at infinity. It behaves so close to negative 2 that you can't tell the difference. So here's what happens. This guy is going to equal a whole bunch of stuff, a1, a2, a3. I'm too lazy to write them out. And then way out here at infinity, what I end up with is negative 1 times negative 2, comma, positive 1 times negative 2, comma, negative 1 times negative 2, etc., comma, etc. So as you can tell, what happens is this thing starts flip-flopping back and forth. So we know that this thing diverges, which is pretty useful. Right on. All right, cool. So sit on that a spell, and we'll let's go ahead and finish up this section, and we can get some. All right, just a couple more real quick things. All right, I want you to think about this. When does, let's go, r to the n. Now this is where it gets really crazy. When does r to the n converge? Converge. When does it converge? Now wait, let's define this more clearly. We're saying that r is a member of the real numbers, okay? And then, so how does this work? We're saying that a sub n equals r to the n. So let's look at one. I don't know, for example, let's do let r equal 2. All right, that would imply, let's put it over here, that would imply that a sub n equals 2 to the n, which would imply that the sequence created by a sub n is equal 2 to the 1, 2 to the 2, 2 to the 3, 2, oh God, these are getting huge. And this guy diverges. Well, that doesn't work. How about r equals half? Well, then a sub n equals 1/2 to the n, which implies that the sequence created by a sub n is 1/2 to the n, which is equal to 1/2, 1/4, 1/8. Hey, this is, now we're making some progress, aren't we? The limit as n goes to infinity of 1/2 to the n is equal to 0, and therefore it converges. Huh. All right, so let's think about this. On the real number line, let's play with the real number line. So this is all the reals, and let's think about this. Is 0 going to converge? Yeah, 0 to the n, because I'm going to get 0, 0, 0, 0. No matter what I plug in, I get 0 back. How about, is 1 going to converge? How about 1? Is 1 going to converge? Well, let's look at it. The limit as n goes to infinity of 1 to the n is equal to, well, 1. Hey, it converges. Sweet. So if you think about it, every number between 0 and 1 is definitely going to converge, because if I pick a a fraction between 0 and 1 and I take it to increasingly larger powers, then I end up with a number that gets closer and closer and closer to 0, because I'm taking a fraction of it which is smaller than 1. So I know for sure that between all of the numbers between 0 and 1 are going to work. Okay, let's see about, let's put -1 out here. And we'll put, oh, by the way, do we also realize, let's use red, do we also realize that all of the values that are bigger than 1 aren't going to work? Because if I take any number larger than 1, right, and then I take increasingly larger powers of it, it's just going to get bigger and bigger and bigger, because you're multiplying by a value that's larger than 1. Okay, so that doesn't work. Okay, so how about between 0 and -1? Well, let's look at -1 first. If I take the limit as n goes to infinity of -1 to the n, well, okay, the sum of -1 to the n, let's look at the sequence, because that just makes my brain hurt. What's it going to be? Well, when n equals 1, it's -1. When n equals 2, it's 1. When n equals 9, and 1, yeah, this does not exist. So we know that -1 is not going to exist. That one's out of there, at -1. But how about values between -1 and 0? Well, look at it. Remember our powerful little absolute value thing? Let's look at a sub n. Oops, sorry. I'm going to change that color real quick. Let's look at a sub n equals -2/3 to the n. Well, sometimes it's hard. That implies that the sequence created by a sub n is equal to -2/3, right? +4/9, -8/27, +16/81, and that can be really confusing to look at. I mean, is it converging? Isn't it converging? Well, however, if we take the limit as n goes to infinity of absolute a sub n, this is equal to the limit as n goes to infinity of 2/3 to the n, which we already talked about over here as being 0, which implies that the limit as n goes to infinity of -2/3 to the n equals 0, and therefore it converges. See, I'm simple country folk. I got to have more concrete, I got to plug numbers in and let my brain sort of play with them. So look, I know that you pick any value between -1 and 1, inclusive at 1, but exclusive at -1, and I'm going to converge. Now wait, is it terribly difficult to realize that any number to the left of -1 or less than -1 is not going to work either? Not only is it not going to work, not only is it going to get bigger and bigger and bigger, but it's going to keep changing signs on us, right? So -2 is going to be -2, +4, -8, +16, -32, yeah, we're not going to deal with that. All right, so let's write up just a little rule. It's not a bad rule to put in your notes. Wink, wink, nudge, nudge. You might see it again. I know that this guy converges, r to the n, converges when, really, when? It's been a long day. It's getting close to finals, guys. I'm getting a little punch drunk. When r lives between 1 and -1, but non-inclusive at -1, but inclusive at 1. That's going to be a useful little piece of information. All right, 2 other quick things, I promise. I'll be quick. I've been yapping way too much. I apologize. All right, let's talk about, this is just going to be a definition. A sequence increases. Now, hopefully your brain, as soon as I said increases, your brain went, ooh, if I match my function to a sequence, then I can determine when a sequence increases simply by using derivatives, right? If the function increases, then the sequence that it's married to must increase as well, right? That's super, super useful. A sequence increases, but we're going to keep it even simpler than that. It's increasing, I should write this out, increasing if a sub n plus 1 is greater than a sub n for every n. For all n. That's hard. Oh, I should say greater than or equal to 1, right? Because we start at 1. Remember, we start at a sub 1, a sub 2, etc., etc. I'll bet you could write a sequence a sub n, I guess I should write it like that, right, is decreasing. Well, when is it decreasing? If a sub n plus 1 is less than a sub n for all n greater than or equal to 1. All right? So, check it out. That's another wonderful little thing. If you start wrapping your brain around the relationship between sequences and functions, if I can show that a function is decreasing, and I know that the sequence for which those values are grabbed on that part of the function must be decreasing as well. Likewise for increasing. I love that stuff. I think it's cool. All right, one more definition, and then I promise I will shut the heck up. All right, a sequence, I'll give you a definition, then I'll give you a theorem, and we'll be done. All right, a sequence is bounded above by, I'm going to say m. Now this is going to look really strange. A sequence is bounded above by m if, and only if, a sub n is less than or equal to capital N for every, look at that, I'm using all kinds of notations here, aren't I? For every n greater than or equal to 1. Now what does that mean? It means, oh man, I'm going to use up too much space here, aren't I? So let's say that this is m right here. This is capital M. That just means that all my a sub n values are less than or equal to that for every single value. Now, students always say, well, is m unique? Absolutely not. Once it's bounded above by any number, I can pick a number slightly larger than that, and it's bounded above by that one as well. Okay? A sequence, let's see if we can write this in the space allotted, is bounded below, I'm not going to have enough room, by, let's use little m, if and only if a sub n is greater than or equal to little m for every n greater than or equal to 1. Now, again, think about what that says. It means a sub n is going to spit out, again, I always think of functions. It's just so much easier for me to wrap my brain around it if I marry it to a function. Here's little m, right? This is the little one. Remember, we were bounded above by big M, and we're bounded below by little m. If all of my sequence values are greater than or equal to m, then I am bounded below by little m. Okay? Last but not least, if a sequence, this is really helpful, by the way, for real analysis, for those of you that are going to end up in that kind of a class. If a sequence is bounded above and below, we say it is bounded. We say the sequence is bounded. That just means that it's hedged in between two values. It's contained between two values. All right, so there's a difference between bounded above, bounded below, and bounded. All right, now, one last theorem, then I'm done. Thank you for your time and your attention. Bell's about to ring, so and I'll let you think about this. All right? Oh, there goes the bell. I'm out.